Hello everyone, welcome to my videos on elementary differential equations. This is video number 3 for chapter 4. In this video, we study high-order homogeneous equations with constant coefficients. So to be specific, the equations we'll be studying here takes the following form. So y is the unknown, and an times y to the nth derivative plus an minus 1 times y to the n minus 1 derivative plus so on and so forth to a1 times y prime and plus a0 times y equals 0. Okay, and here these ai's, they are constants, coefficients. We can handle this in a similar way as we did for the second order equation. We can write out the characteristics, and that will be y to the certain derivative becomes r to that power. Okay, so this term gives us an r to the power n, and then this will give us an minus 1 r to the power n minus 1, so on and so forth, and this term will give us a1r, and this will give us a0 equals 0. So now we have an polynomial of degree n, and we need to find the roots for this polynomial. Okay, so in general, we know from earlier studies that for a polynomial of degree n, one can find n roots. This number of roots n will be counting multiplicity. The roots might be real or might be complex. Okay, and then you can write the polynomial on the left hand side equivalently into this form: r minus r1 times r minus r2 times dot 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 r minus rn equals 0. So this form is called the factorized form of this polynomial, and to find this form is called the factorization of the polynomial. And now from these roots roots r1, r2 all the way to rn, one can then find n linearly independent solutions. Okay, and the way these independent solutions are found, they follow a totally similar rule as for the second order equations, with some extensions to allow a high order. Okay, so let's take a look at the corresponding solutions for each of the roots one obtains. We just list it without really proving them in detail. The proof can be done in a very similar way as what we did for second order equation. Okay, so if you have a root r that is real and it's a single root, it's unrepeated, then this will give you a solution that's e to the rt. Second case, r is a real root and it's a double root, so it's a repeated root. Then it's the same as for second order equation. When we have a double root, we'll have a solution e to the rt, and a second solution is just multiply that by a t. Okay, so these two are the same as we have seen for second order equations. Now, since we have higher order derivatives, so it could happen that this is a triple root. So I put a star to mark this is a new case here. So then it's really very similar. So the first root is the same, and the second root you multiply by t, then you have a third root, you multiply by a further t, and therefore you have t squared times e to the rt. Okay, from now on you can probably see that I could have a real root, I could repeat it m times m is less than or equal to n, and then this will give me m solutions, and e to the rt, and then multiply by t, and then the t squared all the way to the last solution, that's t to the power m minus 1 times e to the rt. Now the next case is when we have a complex root. and we know that they always come in pairs. So if we have a complex pair, that is, real part is lambda, imaginary part is mu, and it can be plus and minus, there are two of them, then it's the same as for the second order equation. We'll get two solutions. It's a product of exponential and sine cosine. Exponential of the real part lambda t times cosine mu is the imaginary part times t. And there is a second solution where you switch cosine to sine function. So this is the same as before, no change. Now, one more case. We could also have complex roots conjugate pair, and it's a double conjugate pair. Okay, so put a star here as a new case. Then this actually would represent 4 roots because there are 2 double pairs, right? So the 4 corresponding functions would be, the first 2 are the same as before, and then we'll pick up 2 more, that is, multiply the previous 2 each by another t, and then we get 2 more solutions. Okay, so if you really want to be general, then a complex root could also repeat m times. So I will not write out. It will be totally similar. You get 1 and you get the second one, and the third one is multiplied by another t, and then the fourth pair will be multiplied by even another t, similar to what we have here. Okay, so we see that once we have found all the roots, it is rather easy to write out the general solution. However, the hard work here would be to find the roots, that is, factorizing a polynomial of power n in general, in which is not an easy task. Okay, let's take some examples. The first example, I wish to find general solutions of this equation. It's a fourth order equation, y to the fourth derivative minus 4y double prime equals 0. That's part A. And part B, we are to find solution with specific initial conditions where the lower derivatives are given at t equals 0. Okay, let's try to solve part A. So we see that we need to write out the characteristic equation and find the roots for that polynomial. So let's write this out. So we'll have r to the power 4 minus 4 times r squared equals 0. Okay? And then let's try to factorize this polynomial. And we see that they both contain the term r squared, so we can take it out. And then what remains is r squared from this term, and minus 4 equals 0. And then we see this term can be further factorized. Thinking 4 is 2 squared, and this gives us r minus 2 times r plus 2, and then times r squared. Okay, so what are the roots of this factorized form? Well, we can look at each of them. This one gives us -1, and this one gives us 2, and this one gives us 0. And then because it's power 2, so it has multiplicity, it's repeated, so it gives us actually 2 roots, r3 equals r4 equals 0. Okay, with these roots given, we can write out the corresponding term in the solution. So for r1, y1 would just be an exponential function. -2 is here. And then r2 is 2, so y2 is e to the 2t. And then we have the case of the repeated roots, where the roots are 0. So y3 is e to the 0t, so which is just constant 1. And then y4 would be just t times y3, which is t. Okay, so once you have found these 4 solutions, then it's rather easy to write out the general solution. You just do a linear combination of them with constant c1, c2, c3, c4 to be determined later by an initial condition. Okay, so since we know what the solutions are, we can plug in y1 here, y2 here, y3 is 1, and y4 is t. Okay, so then this is the general solution. Okay, and then the next step to do is to plug in these 4 initial conditions to find these coefficients C1, C2, C3, C4. Okay, now let's do that. We want to find the constants by the initial data. Okay, so this is the yt from the previous page, and since the initial data contains all the derivatives, let's work out the derivatives. So y prime will be differentiate this term by term. I'll get a -2 in the front for this one, I'll get a 2 in the front for this one. C3 is constant, is gone. Differentiate this one, get me a C4. And then y double prime will be differentiate this one more time. I get a -2 in the front, so I get a 4. And then I get a 2 in the front, I get a 4. And this is a constant, gives me 0. And then one more time we differentiate to get the third derivative. Differentiate this, I get a -2, so I get -8. And differentiate this, I get a 2 in the front, so it gives me 8. Okay, now put in the 4 initial condition. y0 equals 0. Put t to be 0. This term is 0. This term is 1. This term is 1. So we get C1 plus C2 plus C3 equals 0. The second condition is y prime 0 equals 0. Put it in t0. This is 1. This is 1. So I get -2c1 plus 2c2 plus c4 is 0. And the third condition, y0 double prime, is 8. Okay, and then I get, put in 0 here, I get 4c1 plus 4c2 is 8. And I can divide both sides by 4, I get c1 plus c2 is 2. And the last one, y triple derivative is 0, 0. And so I put t0, get 1 here, 1 here. So I get -ac1 plus ac2 is 0. And then this one, I can move one term to the other side, and I drop the 8, and I see I have C1 equal to C2. Now the remaining work is to solve for the 4 constants, C1, C2, C3, C4, using these 4 linear equations. Okay, we see that here actually it's not such a difficult thing to do. We can use the last 2 equations, C1 equal to C2, C1 plus C2 is 2, then we immediately know C1 equals C2 equal 1. There's only one solution for that. And then we can plug these back into the first one to get C3, which is -C1 plus C2, so it's -2. And then put it in here, I'll get C4, and these 2 add up to be 0, so C4 is 0. Okay? Okay, now we can write out the solution by putting in back these numbers. And since C4 is 0, we'll drop the last term. We'll just have the y1, C1, y1, C2, y2, and then C3, y3 is here. Okay, and that's the solution. Okay, let's look at example 2, which is find general solutions for the following equations. We'll have multiple equations we will go through. So let's go through. The first one is y to the 4th derivative plus 4y double prime equals 0. And we want to find general solutions. Okay, so we see that we write out characteristic equation and we look for the roots. Okay, so this gives us R4 plus 4 times r squared equals 0. And then I can take out an r squared, and I get r squared plus 4 is 0. And then the r squared equal to 0 give me double root, r1, r2, they are 0. And then r squared equal to 4 will give me complex roots, actually a pure imaginary, so plus minus 2i, where the imaginary part takes value 2. Okay, and then we can just follow that table we listed earlier. Each solution corresponds to the type of root you have. Okay, so the first one is 1 multiplied by c1, and then the second is t multiplied by c2, and the third one is a cosine 2t multiplied by c3, and then the fourth one is a sine 2t multiplied by c4. So you see, we can easily write out the general solution. Okay, the second equation, y triple derivative minus y equals 0. We want to find the general solution. So again, let's find the characteristic equation. So we have r to the power 3 minus 1 equals 0. And then this, we know there is a root when r equals 1, this is 0. So there is a root, there is a factor r minus 1. Taking out that factor, what remains is r squared plus r plus 1. Okay, so, and then the first factor gives us one root, that's r in 1 is 1. And then this, what's remain here is a quadratic polynomial, and we can use the formula to find the roots, which turns out to be complex roots. So the real part is negative half plus minus I times imaginary part is square root of 3 over 2. Okay, so once the roots are done, we can just write out the general solution. So R1 will correspond to e to the t times c1, the first solution. And then the second one would be, the second and the third would be exponential of the real part, and then sine and cosine of the imaginary part times t. Okay, so let's pull out the exponential part outside, and then we have c2 times cosine times the imaginary part times t comes from here, and then c3 sine times this imaginary part times t. Okay, so this is the lambda and this is the mu. I just wrote out the formula with lambda equal to that and mu equal to that. Okay, here is another equation. Y to the fourth derivative plus 8y double prime plus 16y equal 0. Okay, quickly one can write out the characteristic equation. And then here we see that if we treat r square as a variable, we see this is a perfect square. So this is r squared plus 4 square. Okay, and then we see that r squared plus 4 gives us two complex roots plus minus 2i. Since this is to the power 2, then they are both double roots. So we have r1, r2 both equal to 2i, and r3, r4 equal to negative 2i. Okay, so this is a new situation which we have never seen for second order equation. That is, we have double complex roots. Okay, we can just follow the table of the general solution. Then we'll have 4 solutions. We'll do linear combination. y1 would be cosine 2t, y2 is sine 2t, and then we have a y3 and y4, which is just multiply each of them by a t. So that t multiplied to cosine and t times sine. Okay, so all rather straightforward. So here is another example. Y triple prime plus 3y double prime plus 3y prime plus y equals 0, assuming that's the equation. Now we will write the characteristic equation. So that's r cubed 3r squared 3r plus 1. Okay, and then if you are fluent with the Pascal triangle, you know that this is a triangle. This is what, let's say 1 1 1, and the square will be 1 2 1, right? And then the cube will be 1 3 3 1, and that's exactly what we have here, 1 3 3 1. So it's r plus 1 to the cube. Okay, now here is also a new situation. We have a root negative 1, which is a triple root. Okay, so triple root or whatever, we know how to handle, we can write out the general solution. So the first one is e to the negative t, and then second solution is t times e to the negative t, and the third one will be t squared e to the negative t. And if you really like to write it in a neat way, you can take out e to the negative t and collect these polynomial term. You get c1 plus c2t plus c3t squared. Okay, so the last example, it's a little bit tricky. This one, the tricky part is in finding the roots, but not bad, so let's go through it. So y to the fourth derivative plus 16y equals 0, finding general solutions. Okay, so let's write out the characteristic equation. That is r to the fourth plus 16 is 0. So this means r to the fourth is negative 16. And if I consider myself in the complex plane, this negative 16 is 16, which I can write as 2 to the power 4 times e to the I pi. Okay, let me draw a picture to illustrate that idea. So in a complex plane, this is the real part, and this is the imaginary part. Negative 16 would be here, right? So it's a negative 16 and the angle is pi. Okay, that's why we can write negative 16 as this complex number. So the advantage of expressing this as a complex number is that now it's easier to find the roots, because we're going to take a root of 4. Okay, so we can write out 4 solutions, and we call it Rk. K is from 1, 2, 3, 4, and this we have learned in taking roots of complex numbers. So this would be a complex number with radius r, and it will live on this circle with radius r with these angles. And then these angles differ by pi over 2. So let me draw a picture. So where are these Rk's? So again, let's look at the let's draw red. So again, I am in the complex domain. This is the real part, and this is the imaginary part. And I'm looking at a circle with the radius 2. Okay, so let me attempt to draw a nice circle, radius 2. Okay, so your the right hand side is e to the I pi, this angle. So if I divide this by 4, I get pi over 4. So then the first number, the root here, would be r1 here. Okay, and then the second one will be add a 2 pi on this angle and then divided by 4 again, so I get 3 over 4 pi. So this will be r2, and then this will be r3 on here, and this is r4. Okay, so if we label them like this, and we see that r1 and r4 are complex conjugate pair, and r2 and r3 are conjugate pair. Okay, and then we want to write out the real part and the imaginary part. Let me use blue here. So since this is radius 2, then if you look at the intersection here, it's square root of 2, and then the intersection here also is square root of 2. Okay, so here this will be negative square root of 2, and then this is negative square root of 2. Okay, so we can have 4 roots here. Then one would be with the real part square root of 2, and imaginary part square root of 2, a complex pair. And then another one is with the real part negative square root of 2. Okay, So sorry for this drawing, a bit messy. Now let's write out the solutions. Okay, so here I wrote in words. We can find them just in a complex plane on the circle. Okay, from the circle we had before, now it will be clear for us that we have one set of root is root 2 plus minus I root 2, and then another pair is negative root 2 plus minus I root 2. Okay, since both of these are just single roots, they're not repeated complex roots, then we can just write out the solution. So this one will contribute an exponential function and the sine and the cosine. So sine and cosine is with square root of t, and the exponential function term is square root of t here. Okay, and then c1, c2 are arbitrary constant. And then for this pair of roots, it will contribute something similar. And then now here the real part is negative square root of 2, so the exponential function will be decaying. And then we have a sine and cosine with arbitrary constant c3, c4 in the front. Okay, and that's it for all the examples I wish to give for this case. And don't be scared of factorizing polynomials. Okay, they're very complicated ones are not really required from you. Okay, we will only deal with rather reasonably simple ones. Okay, so that's all for this video, and I hope you enjoyed it. I'll see you next time.